everybody, and welcome back to Environmental Science 101. Here we're going to do our carbon cycle. So, when we talked about nitrogen and the nitrogen cycle, I didn't say it right, but we did the more complicated one first. Carbon cycle is going to be more simple by comparison. Probably a good thing. I start off with a diagram here. We're actually going to come back to this one once we know a little bit more about it, right? I like this diagram, though it's a good jumping off point because it is not busy. Doesn't make me feel overwhelmed. Good. All right, we have this thing called carbon. Carbon comes in many forms. I would hope that we've heard of it, our sixth element on the periodic table, right? So we talked about C, N, O, and H, right? Carbon, nitrogen, oxygen, and hydrogen as being 95% of all the living stuff and everything that goes on with life. And that's pretty much going to be true, right? And we might also remember, right, phosphorus and sulfur along with calcium going to be our things of secondary importance, broadly speaking. Okay, so we have reviewed our nutrients a little bit. We got carbon, right? Sixth element. It's going to be a non-metal. It's going to be, well, depending on what form it's in, some sort of solid at room temperature for the most part. Comes in forms that we've heard of for sure, right? So diamond, this thing here. If we were to write out the chemical formula of diamond, it's so complicated. It looks like, well, I'll draw it, right? It's like that. Yeah, it's literally just C. It is all carbon. Graphite, right, which is commonly in pencil lead. It's a mixture of graphite and clay. This one is also chemical formula, really complicated. It's just going to be big C. As a fact, maybe fun, maybe not, graphite is actually more stable than diamond is at surface conditions, right, like we have here on Earth. Diamond is more stable deeper in the Earth, right, but actually all diamonds up here at the surface are very slowly over, I want to say hundreds of thousands of years, slowly turning into graphite. So I'm sorry to say diamonds are not forever, so stop doing that. Okay. This is essential to all life, right? It forms rings and chains, right? Rings providing structure and chains that you can extend as far as you want in order to make things as big as you want. Really great for building all sorts of stuff. And in fact, this word organic, right, for our context, not like buying food that's organic, right, it's going to mean that it has carbon, right? And it is simply unlike any of our other elements. And so it's one of the nutrients that we need to track here. Comes in many forms, could be solid like we talked about, could be gas form, right? Especially carbon dioxide in our atmosphere. Okay, so we might know something about photosynthesis already, so I'll go fast. If you don't, you might have to pause here and spend a little bit of extra time, right? So plants are going to take in CO2 from the atmosphere, which we're going to imagine as being this big open reservoir with so much carbon in it, right? That we can just pull from it and pull from it, right? Okay, they are going to turn it into a more usable form of sugars, right? Organic molecules with stored chemical potential energy. This is kind of analogous to this process of bacteria who fixed the nitrogen so that plants could use it. Here, we're taking carbon and fixing it, turning it into a form that is usable for all the stuff that is going to eat the plants, right? And then the nutrient is going to make its way up our food chain, up our trophic levels. Specifically, we need to talk about what happens with carbon, right? So we've got photosynthesis, all right? Carbon dioxide, water, and energy go in. What comes out is oxygen and sugars, right? Which is going to have the carbon from the carbon dioxide, but in a different form that is better usable for everything else that comes and eats the plant. Okay, so sunlight, carbon dioxide, and water go in. Oxygen and sugars go out. With cells, animal cells, which go through this process of respiration, where they make energy, it is going to be the process in reverse. Now, I'm cutting out some of the details here, right? But this process whereby the cells make energy, this thing that we talked about that's so important, is going to be essentially the exact opposite process. I mean, look at this. Okay, photosynthesis, we got carbon dioxide and water, plus energy in makes glucose, which is our sugar, our good form of carbon, and oxygen. And then now the cell is going to take in glucose from this plant that you just ate. It's going to take in glucose and breathe in oxygen, right? It's going to release energy and wind up with a product of carbon dioxide, which you exhale, and water, right? So we can see, right, our carbon is passed up through the food chain, like our nutrients, from producers to consumers to other consumers. It's going to be released back into the atmosphere by consumers, which exhale, and also by decomposers, which break stuff down. Now, not all of the carbon gets put back into the atmosphere, right? Some of it gets stored for later. Actually, some of it gets buried. A lot of it gets buried and becomes these things called carbon deposits. We're going to talk about two kinds of these, all right? Okay, so We've got our animals, they're living, they're eating plants, they're going through this process of respiration, they're exhaling, right? But sometimes when they die, some of the carbon that is in their body is not returned to the atmosphere. It is buried. And when it gets buried deep enough, all right, it's taken out of circulation, right? It's taken out of the atmosphere. We could also understand in the context of climate change that burial of carbon is a good thing and that unburying it is going to be bad. And we'll just leave it at that for now. So carbon deposits are going to come in two forms, and something that we should be aware of, right, is just the sheer amount of carbon that is going to be stored in this stuff. All right, the pictures don't necessarily do it justice, but this is so much matter, so much material that is going to be buried in both forms here, really. So one form is going to be fossil fuels, which we've heard of, right? It's going to be in the form of hydrocarbons. Hydrocarbon sounds like a complicated word, but it's exactly what it sounds like, right? It's going to be things with carbon and hydrogen in them and nothing else, right? Long chains of them. This is going to include oil, natural gas, right? The other way that we can have carbon deposits underground is through limestone, right? Which is going to store carbon and oxygen, though we don't necessarily care that it stores oxygen for now, and put it into the form of these rocks, right? So these are limestones. This looks like southern China. I could be wrong, but it very much looks like the limestones they have down there, which dissolve and make these big, beautiful caves. Lovely part of the world. Also true for our chalk cliffs, our famous cliffs of Dover in England, right? This is also made out of limestone. This is made out of dead life, right? So two different processes of formation for these fossil fuels, right? So we can imagine, right, a big tree that is in a swampy area. The tree dies, falls down into it, right, and sinks to the bottom of this really still, stagnant water that is never getting circulated around. Now, because it's still stagnant water, there is no oxygen at the bottom of it to break the tree down. And so as stuff piles in, right, sediments and other trees, right, it gets buried into the ground without ever having decomposed, right? And once it gets cooked and smushed and processed, very technical terms for what happens underground, it gets turned into hydrocarbons and eventually becomes oil and gas deposits. Most importantly, right, carbon was put into it by photosynthesis and then taken out of circulation as it was buried. With limestones, right, and carbonate rocks, to use the bigger term, what we're going to have is mainly marine organisms, so sea organisms that take in carbon and use it as part of their shells, use it as part of their bones and teeth and other hard parts. When they die, it sinks all the way down to the bottom of the sea floor, and it gets buried, right? Buried under sediments, buried under other dead things, gets turned into carbonate rock, and now instead of our carbon being in the atmosphere, it is stored inside of this. It's important for us to remember there is a lot of carbonate rock. There is a lot of fossil fuels. These are both massive, what we might call reservoirs of carbon. Awesome. So now we can put it all together. And again, I don't love these diagrams, but, you know, even minus the stupid cartoons, this one's actually not that bad. Okay. So we got carbon in our atmosphere to start with, atmospheric carbon in a big reservoir, right? It's going to be taken up by plants, primarily, right? Plants are going to be eaten by animals who are going to breathe it back out in that process of respiration, but it also might be buried into the soil, right? Now, some of it is going to get decomposed, some of it is going to get cooked and turned into fossil fuels, which are burned and put back. Some of it is going to be taken up by marine organisms and buried, right? But what we have is this circulation of carbon through all these different reservoirs. And importantly, something like this, as complicated and busy as it might seem, right, we could actually, if we wanted to, maybe in a future unit, go in and specify numbers, right? So exactly how much carbon is in the atmosphere, how much is in the limestone, how much is in the fossil fuels, and how much is being transferred from one part to another. And we can start doing this kind of accounting, right? It's like budgeting with carbon for the whole world, which could be really, really important and useful for us to do if we were trying to figure out how much carbon is in all these places and how to get it out of the atmosphere. So this serves as a framework concept for when we do climate change. Awesome. And just to touch on this a little bit, we can look at variations in atmospheric carbon dioxide over time. This is stretching back not very far into geologic time, basically our last, well, 500,000 years, which, as we know, right, would be a fraction of a percentage of all of it. But just looking at these recent cycles, which are driven by primarily the quirks and oddities of Earth's orbit on the scale of tens to hundreds of thousands of years, right? We notice that carbon dioxide has a cycle, right? It's this mix of big waves and little waves in there, right? The carbon dioxide cycle lines up directly with our temperature cycles and ice age cycles. So times when carbon dioxide starts falling low, we get an ice age. When it spikes back up, we have the end of the ice age, right? So we have it spike back up, right? Causes a corresponding spike in temperature, right? And then it slowly falls, and it spikes back up, and it slowly falls. And importantly, our current carbon dioxide level, which actually this graph is a little bit dated, our current level would be something like here, right? We notice does not fit this trend. It's a little bit naive for me to do what I just did, but we'll see why even being wrong about this leads to the same conclusion in more detail. So that is going to cover it for our carbon cycle. Next we do soil and then soil pollution, more on the human side of it. Thanks.